From the ground, it almost looks like a mistake. A passenger plane is descending toward the runway, but its nose isn't pointing along the runway markings. It's pointing off to the side. The fuselage is at an angle. One wing seems to be thrust out into the wind, and the wheels are approaching the tarmac as if they're about to be turned out by lateral force in a second. The plane weighs tens, and sometimes even hundreds of metric tons. Its speed is still enormous. There are only a few meters left to the ground. And it is precisely at this moment that the pilot must transform the aircraft, flying sideways, into one moving strictly along the runway. Not in a minute, in a matter of seconds. How does the landing gear withstand such a touchdown? And why is the aircraft forced to approach the runway in a position that seems incorrect to an outside observer? At first glance, the answer seems obvious. The wind pushes the plane to the side, so the pilot simply turns the nose into the wind. That's true, but it only explains the surface-level picture. The pilot's main task is not to point the nose toward the runway. The main task is to keep the entire plane moving over the ground exactly along its center line. And these are not the same thing. The plane flies within an air mass. If this mass is moving across the runway, it carries the plane along with it. Therefore, the direction the nose is pointing and the direction the aircraft is actually moving relative to the ground may differ. The pilot turns the aircraft into the wind, just enough so that the lateral drift caused by the wind is offset by the lateral component of the aircraft's own speed. Imagine a boat crossing a fast-flowing river. If you steer it directly toward the opposite bank, the current will carry the boat downstream. To arrive exactly at the desired point, you have to turn the bow against the current. The same thing happens with an airplane, except that instead of water, there is moving air, and instead of a bank, there is a narrow strip several kilometers long. This technique is called a crab approach. The name accurately describes the visual effect. The airplane is pointing in one direction but moving slightly in another. However, it does not drift uncontrollably. On the contrary, its flight path can remain almost perfectly straight. The stronger the crosswind, the more noticeable the angle between the aircraft's longitudinal axis and the runway. This is precisely why the video makes it seem as if the pilot is missing the target, even though he is actually maintaining the center of the runway much more precisely than a straight flight without correction would allow. But this raises a more serious question. If a crab approach keeps the aircraft so well aligned over its center line, why not maintain that angle all the way until touchdown? Because air and concrete require the aircraft to be in different positions. While the aircraft is flying, the wings and tail calmly maintain the correct angle relative to the wind. But the moment the wheels make contact with the runway, a rigid connection with the ground is established. The wheels want to roll in the direction they're pointed, that is, along the aircraft's longitudinal axis. Meanwhile, the inertia of the entire multi-metric ton aircraft continues to carry it along the runway's direction. If the angle between these directions is too large, the tires begin to experience strong lateral friction. The struts experience a bending moment, and the landing gear mounting points experience a sudden transverse load. The landing gear is designed to handle lateral forces, but that does not mean the aircraft can be dropped onto the runway at any angle with impunity. And this is where the most precise phase of the landing begins, leveling off before touchdown, or reducing the crab angle. As the aircraft enters the final meters of descent and the pilot begins to gently raise the nose, reducing the vertical speed, he simultaneously presses the rudder pedal. The tail swings out, and the nose aligns with the runway. But rudder alone is not enough. As soon as the fuselage straightens out, the previous wind compensation disappears, and the aircraft begins to drift sideways again. Therefore, the pilot applies a slight bank toward the side from which the wind is blowing. The wing on the windward side drops slightly. The lateral force keeps the aircraft from veering off course, while the fuselage remains nearly parallel to the runway. The result is a brief combination of two movements. The rudder aligns the nose, and the ailerons prevent the wind from carrying the aircraft off course. From the outside, this transition may look abrupt, but it is actually executed with great precision. Leveling off too early will allow the wind to blow the plane off course before touchdown. Leveling off too late will leave a large angle between the wheels and the direction of travel. Too much bank will bring the wingtip or engine too close to the ground. Too little bank won't stop the crosswind drift. That's why the pilot doesn't just execute a single, smooth turn. He continuously balances the turn angle, bank, speed, wind gusts, and altitude above the runway. On some types of aircraft, a slight residual crab angle is permitted at the moment of touchdown, but it must remain within the limits of the procedures and capabilities of the specific aircraft. The goal is not a geometrically perfect picture, but rather to keep the lateral speed and loads on the landing gear under control. Now it becomes clear why, in strong crosswinds, one main landing gear leg sometimes touches down before the other. When the pilot maintains a slight bank into the wind, the upwind leg ends up lower. It is the first to bear some of the weight, then the second leg lowers, and only after that does the nose gear touch down. To a passenger, this may feel like an uneven touchdown, but from an engineering standpoint, this sequence is often preferable to attempting to lower both main landing gears simultaneously at all costs. Moreover, the design of a commercial airliner is tested not only for symmetrical landings. Certification standards separately address touchdown on a single main landing gear leg and combinations of vertical, longitudinal, and lateral loads. In other words, lateral force acting on the landing gear is not an unexpected emergency scenario, but rather one of the design conditions. However, the landing gear itself is not just a thick metal leg. At the moment of landing, it functions as a system that distributes energy and forces in multiple directions. The shock absorber compresses and dampens the primary vertical energy of descent. The air springs deform, increasing the duration of the impact and smoothing out short load spikes. The wheels quickly spin up to the aircraft's speed. Lateral forces are transmitted through axles, levers, struts, and robust mounting points into the wing or fuselage structure. Therefore, the landing gear is designed to withstand more than just top-down impacts. For transport aircraft, design lateral loads are specified separately, and operating conditions in which one side is loaded more heavily than the other are verified. But this strength has its limits. This is precisely why, in the event of an unstable approach, excessive drift, or too steep an angle of attack, the pilot must go around for a second approach, and after an unusually hard or sideways touchdown, the aircraft may require a technical inspection. The battle against the wind doesn't end after the first touchdown. As long as the speed remains high, the wings continue to generate lift, and a gust can lift the upwind wing and relieve pressure on the wheels. The pilot continues to apply a roll control against the wind, although as speed decreases, the aerodynamic control surfaces gradually lose their effectiveness. The rudder helps maintain course, after which the wheels, brakes, and nose gear control begin to play an increasingly important role. On modern airliners, spoilers deploy, reducing lift and transferring most of the aircraft's weight to the landing gear. Only then does the aircraft finally transform from an aircraft into a ground vehicle. But this transition does not happen instantly. For several seconds, the aircraft is simultaneously subject to aerodynamic forces and the friction of its wheels against the concrete. That is precisely why a side-on landing is neither a mistake nor a dangerous maneuver. It involves the coordinated control of two different directions, where the aircraft is pointing and where it is moving relative to the ground. During the final approach, the crab angle maintains the correct flight path. Before touchdown, the rudder turns the fuselage parallel to the runway. A slight bank prevents the aircraft from drifting off course. The landing gear absorbs the remaining vertical and lateral loads, for which it is designed in advance, and if the wind, gusts, or the aircraft's position exceed safe limits, the correct decision is not a heroic attempt to land the aircraft at any cost, but to go around for a second approach. This is the hidden beauty of such a landing. From the ground, it looks as though the huge airplane is correcting its own mistake at the last moment. In reality, there was no mistake at all. It was following a precisely calculated trajectory the entire time. It's just that its nose, the air mass, and the ground were all moving in different directions. The pilot doesn't fight physics or force the aircraft to violate its laws. He uses these laws in sequence. First, he allows the plane to be turned into the wind. Then he turns it toward the runway. And after touchdown, he transfers control from the wings to the wheels. And the next time you see an airliner approaching the runway almost sideways, the main question will no longer be why it doesn't break its landing gear. Something else is far more interesting. How many more complex engineering solutions are hidden in those few seconds that seem like a routine landing to a passenger? If you were curious to learn why an airplane approaches the runway sideways in strong winds and how the landing gear handles this challenging situation, subscribe to the channel and give it a like. There are even more engineering stories to come, in which seemingly strange movements are actually driven by precise and well-thought-out logic.